state qubits in diamond film. So here you can see, based on different beam energies, how you can position the qubit and look at its fidelity. So second science highlight. Oh, I think the slide just kind of froze. Apologies. This is not my laptop, but let me see if I can fix it. Okay. Oh, there we go. Okay, so kind of beyond some of these color centers in materials that are promising spin qubits, you can also create integrated two-dimensional quantum materials with silicon heterostructures. So here's just one example of a high quality factor resonator that can be used for electro-optic control. For example, in this case of the either optical transmission or the emission of qubits, you can get fully reconfigurable, say, beam steering of an optical beam based on applying voltages to nano antennas in a silicon nanostructure. And then these can be interfaced with two-dimensional materials that host, for example, spin qubits or Moire excitons, either interlayer or intralayer excitons that basically emerge from the different valleys in the band structure of the two-dimensional material. So in the band structure of these two-dimensional materials, you have both a plus K and a minus K valence and conduction bands, where if you illuminate with circularly polarized light, you can basically get spin locking. So the electron spin gets coupled to the photon spin. The challenge with a lot of these materials is that they only generally work at low temperature, because otherwise you get inter-valley scattering. So basically you get spin decoherence from the electron spin in one valley, say the plus K valley, coupling to the minus K valley via phonons. So some research at Stanford and SLAC are basically integrating these two-dimensional materials with those reconfigurable silicon nanostructures enabled in order to be able to control the inter-valley scattering. So one of the shared facilities on campus allows for large area transfer of two-dimensional materials using basically kind of gold tape exfoliation of these two-dimensional materials. You can then put large areas here, almost centimeter scale areas of monolayers of two-dimensional materials on these silicon devices. And then you can see how the silicon, by a combination of how the nanostructure controls light and also how it controls the strain in material, gives rise to much better coherent processes and photoluminescence in these two-dimensional materials. And here's just one example of how one of the high quality factor silicon cavities combined with these large area 2D materials is enabling better coherent properties in valley polarized emission.